Welcome to the second part wherein we'll discuss some more questions based on the PI and PK values. So the enzyme has glutamate at 76th position and aspartate as a 52nd position. Generally, if there is a peptide and if the glutamate is in the 76th position and aspartate is at the 52nd position, it's impossible for them to meet, and that is why the proteins go into folding. So when they go on undergo folding, if the aspartate is at this position and the glutamate is at this position, they tend to meet. And when they both meet, active site is formed. So now in this question, they are telling for the active site to be there, the aspartate should be deprotonated and the glutamate should be protonated. They have also given the value for aspartate as 4.5 and for glutamate as 5.6. Now they are asking us what is the pH where enzymes will show maximum activity. Okay, let's just find it out then. So for the aspartate should be 4.5. pH deprotonated means generally aspartate will have carboxylic group and glutamate will also have carboxylic group. So at pH 4.5, it will be in the below 4.5, it will be in the protonated form, but above 4.5 it will be in the deprotonated form. So we want it in the deprotonated form. So just increase the pH beyond 4.5. Just increase pH. And in the case of the glutamate, carboxylic is in the protonated form. So below 5.6 it will be in the protonated form, but above 5.6 it will be in the deprotonated form. Hence you just need to, if you want it in the protonated form, it should be below 5.6. Here you have to below 5.6. So just check for any value which is above 4.5 but below 5.6. What is that value? This value 5.05. So this is the answer. So if you forgot how this protonated and deprotonated works, it's very simple. So generally the amino acid is in the protonated form. COOH, C, you have an R group, then you have a H group, and then you have a amino group NH3+. Over here everything is protonated, everything is having a proton. So this is the value. So this is the PI of an amino acid. If you consider for an amino acid it's PA, but if you consider for an individual functional group, then it is referred to as a PK. Either PK1 or PKA or PK2. All the next question now. Choose the correct statement from the following. Disulfide bonds in a 20 residue peptide can be formed only if cysteines are adjacent to each other. So they're telling that in a peptide, only if cysteines are side by side can they form a disulfide bond. But no, absolutely not. Sometimes, not sometimes, most of the times, an enzyme folds, and when an enzyme is folding, the two cysteines which are far away from each other also tend to form a disulfide bond. So why is it that only they should be beside? So the statement is wrong. The amino acid isoleucine has only one chiral center. Now remember over here that isoleucine and also threonine have two chiral centers. I'll draw an isoleucine structure to show you the same. So isoleucine is having the normal carboxylic group which is connected to a carbon, a ammonia group, a hydrogen, and an R group is consisting of CH3, H, H to balance the valency, H, H and H. So if we see over here now, this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4 and this is carbon 5. Now, so for this carbon 2 is carbon 1 is not a chiral carbon because it is not having 4 different groups. Looking at the carbon 2, this one is a different group, this one is a different group, the total, this one is a different group and this one is a different group. So this is a chiral carbon. And if you look at carbon 3, it is having CH3 over here, it will have one more hydrogen over here. So this is different hydrogen, CH3 is different, and this whole group is different, and this whole group is different. So now it is having two chiral carbons. And if you look at fourth one is not a chiral, and fifth one is also not a chiral carbon. Hence, it has two chiral carbons. And do you remember the Van 't Hoff's formula? Wherein I have told you to find the stereochemistry, you apply the simple formula, that is 2 power n, where n is equal to number of the chiral carbons. So it is 2 power 2. We have two chiral carbons over here. One is at the C2 position and the other one is at the C3 position. So when you apply this, you get 4. Hence, you get 4 enantiomers for both isoleucine and threonine. Next, so choose the correct statement. This is wrong. Next, both bases and sugar contribute to chirality of nucleic acids. Now, if you do not know whether this statement is right or wrong, anyways, the statement is wrong. Because chirality refers to being attached to 4 different atoms. The sugar is not. So, if you don't know whether this is right or wrong, just go by elimination method. So, we'll just keep this aside for now. We'll read the fourth one. The pI of aspartic acid is less than that of glutamic acid. We have already read. The pI of aspartic acid is approximately 3.7 and glutamic acid is approximately 4.3. So yes, the pI of aspartic acid is definitely less than glutamic acid. Hence, this is the right answer. Now the second question. Which statement best describes the pKa of amino groups in the protein? Okay, so they're telling pK of amino groups. Done. The pKa of alpha amino group is higher than the pK of epsilon amino group. Now you definitely understand when they're meaning epsilon, they mean lysine. And what is the pK value of lysine? It is 10.5. What is the pKa value of alpha amino acid? It is approximately 9.69. So what are they referring? pK of alpha amino is higher. No, definitely not. pK of alpha amino group is lower than pK of epsilon. Yes, correct. This is correct. pK of alpha amino group is same. No. pK of alpha amino group is higher than. No, again not. Okay, they are referring to guanidinium sine chain. That's why you have to read the whole question. Anyways, the guanidinium is 12.5. So this is also wrong. So the correct option is 2 and fourth one over here. Now let's solve some more questions from Pathfinder. Which of the following statement is not true about amino acid? Only 22 standard amino acids are used in protein synthesis. Currently only 22 are used. This is correct. All amino acids exist in two stereoisomeric forms. Amino acids have N-terminal, C-terminal, R groups. Yeah, this is also correct. Then there are more than 300 different kinds of amino. Yes. So even though there are only 20 standard amino acid plus 2 newly introduced, that is selenocysteine and pyrrolysine amino acid, we also have more than 3 different types of amino acids which are also called as the non-standard amino acids. So now if we come back to the second statement, all amino acids exist in two stereoisomeric forms and we have to find out which is not true. So if we look or remember the glycine structure, glycine's R group is only H. So this is not having any stereoisomerism because the H is repetitive. There are two hydrogens. So to have a stereoisomer, we need a chiral carbon and glycine is not chiral carbon. Hence, the option is B. Next. Which of the following amino acid, if added to a acidic solution, will have buffering action at the physiological pH? It's histidine, as we have already discussed, because the pH is equal to 6. And this is approximately equal to the physiological pH. And hence it has a greater buffering range. The peptide bond in protein is, so if you remember the peptide bond, it happens between the carboxyl group and the NH group, and it is mostly present in the trans conditions. So the peptide bond in proteins is non-polar but rotates to 3 preferred dihedral angles. Planar but rotates to 3 preferred dihedral angles. We have not talked about this, but let me tell you, it is planar. Planar is, it is having a, it's present in a single plane. It will not move. This angle is omega. There is no movement over here. Only cis to trans. Only it will either have in the opposite directions or the functional groups will come to the same direction. Next, non-polar and fixed in. This is not non-polar. This is polar. So this option is wrong. It's also non-polar, so this option is wrong. It's planar and usually found in trans configuration. So this is the right answer, D. The isoelectric point of a protein is defined as, what is the isoelectric point? The pH at which the net charge on the molecule is 0. This is absolutely right. So Pi is pH at which the net charge on the molecule is 0. Again, as we have discussed, it's because of the plus and minus charge on the ammonia group and also the carboxylic group, which gets cancelled out and 0 charge. This is the correct answer, A. The pH at which also, this doesn't make any sense at all. Let's move to the next question. So this is already solved. Which one of the following is the major force of attraction that stabilizes the three-dimensional structure of globular protein? So if there is a three-dimensional protein, what is it stabilized by? Is it peptide bond? Is it hydrogen bond? Is it van der Waals or hydrophobic? It's generally hydrophobic forces, because the inside forces, the forces which are held tightly, are the hydrophobic interactions, because they do not want to be exposed to the polar conditions. So they are held tightly, and hence the three-dimensional structure is well kept. Next, which of the following amino acids have side chains that are negatively charged under physiological conditions near pH 7? Have side chains that are negatively charged. So only two amino acids are there. One is D and the other one is E. That is aspartic acid and glutamic acid. So tryptophan, which is that are negatively charged. Only aspartate is there, so this is the answer. Over here, this is the answer. Over here, this is the answer. Okay, if a polypeptide has 400 amino acids, what is the approximate mass? So each amino acid weighs approximately 110 Dalton. Right. So if the polypeptide has 400 amino acids, that means 110 into 400. What will be the answer? 44,000 Daltons. This is the answer. Which of the following amino acid residue is likely to be found inside the water-soluble protein? So if there is a protein, similar to this condition, if there is a protein and it is water-soluble, so hydrophobic groups will go and hide inside. So we have to find what are the hydrophobic groups. Arginine is positively charged. So this is polar. Then aspartate is negatively charged. This is also polar. Histidine is positive. Only isoleucine is 0. It is because it is hydrophobic in nature. It will tend to go inside, and hence this is likely to found on the inside of a water-soluble protein. Next, if the average molecular weight of one amino acid is 128. So why did I tell 110 over here then? Generally, the average weight of an amino acid is 128. But when a peptide is formed between two amino acids, amino acid 1 and amino acid 2, I have already told that a water is lost. When a water is lost, water's molecular weight is 18 AMU, atomic mass unit. So 110 minus 18, this will give 128 minus 18 will give 110, and hence I have told the amino acid weight is 110. Whenever you are considering an individual amino acid, take it as 128, but if it is in a peptide, take it as 110 Dalton. And AMU and Dalton are approximately equal, so it will be 128 Dalton or 128 AMU. Okay, so the average molecular weight of one amino acid is 128, and the molecular weight of a linear oligopeptide made up of 10 amino acids is approximately. Okay, let's calculate this. Now we have amino acid which is made up of, a peptide which is made up of 10 amino acids. So amino acid 1 plus amino acid 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So to make up this, one water molecule is lost. For this, one water molecule is lost. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Hence 9 water molecules are lost in making up a linear peptide. So always remember this rule. If you are making a peptide with 10 amino acids, then only 9 water molecules are lost. So 10 minus 1. If you are making it up with suppose 100, then you are forming 99 peptide bonds. Hence 99 water molecules are lost. So you just have to subtract it. I'll just erase everything. Okay, so for 10 amino acids, each amino acid weighs 128 Dalton. So 128 Dalton into 10. And as 9 peptide bonds are formed, we have to just minus 18 into 9. So 128 into 10 is 1280 and 18 into 9 is, so it is 162. And so 1280 minus 162 is 1118. So this is approximately equal to 1100. So this is the answer. Next, a peptide has a sequence. So now we have a good sequence. What is the net charge? So this is a really good question. So let's write down the sequence first. A peptide has a sequence where it is having GLU is glutamic acid, then it is having histidine, then it is having tryptophan, then it is having serine, then it is having glycine, then it is having leucine, then leucine is connected to arginine, arginine is connected to proline, proline is connected to glycine. Okay, so the first thing we will mention the N and the C terminals. So let's start from N terminal, NH3 plus, and before that we'll cancel out whatever is non-polar. So if we look at this, glutamic acid is, yes, it is polar, histidine polar, tryptophan is not, tyrosine is but not tryptophan, serine is not, glycine is not, leucine is not, arginine is yes, proline is not, again the glycine is also not. So let's just cancel them out. Now let's write with whatever is remaining. Then glutamic acid, glutamic acid is D. Oh sorry, glutamic acid is E, aspartic acid is D. Then histidine is H. Then after them you have arginine. Arginine is R. Then you have the C terminal. Let's write the C terminal which is attached to the glycine. Let's just strike off the glycine. So I'll only write the C terminal. COOH. So the first step is we will identify the each and every amino acid, cancel out whichever is non-polar or whichever is not having any pKa values. Then we'll write from N terminal to C terminal, and everything should be protonated. Here amino acid is protonated and also carboxylic acid is protonated. Now we'll write the side chains. The glutamic acid is having COOH as a side chain. Histidine is having NH3, ammonia only. Arginine is also having ammonia only as a side chain. Okay, now the second step. What we'll do is, what is the pH they're asking? At pH 11. So we'll mention the pH 11. And what is the pKa values? We'll just write them down. For ammonia, pKa is, sorry, pK2. This is pK2 value. So pKa value is 9.6. For glutamic acid, it is approximately 5 or 4, somewhere there, it doesn't matter. Then histidine is 6. Arginine, it is 12.5, and carboxylic acid of the amino acid, it is just 2.43 or somewhere over there. Now if we are considering the pH, pH is 11, so it is greater than Pi, hence it is deprotonated, so it will become NH2. This will become NH2, and this is also deprotonated, so it will become COO minus. Then look at the histidine, it will also be deprotonated because it is just 6, the Pi is just 6, pH is greater than that, so this will also be deprotonated. And if you look at arginine, this is 12.5. For this the pH has not surpassed the Pi, hence this is already protonated and it will remain protonated only, so it will be NH3 plus only. And then the carboxylic acid's Pi is 2.43, so pH has already crossed the Pi, therefore it will also deprotonate. Now let's do the charge calculation on this. So what is the charge calculation? NH2 is 0 plus COO minus, so minus 1 charge, plus NH2 is having 0 charge, plus NH3 plus is having a plus 1 charge, plus carboxylic is having a minus 1 charge. So now let's just add this up. Minus 1 plus 1 is cancelled out, then we have only minus 1. So the answer for this is minus 1. Option D is the correct answer. So from this, like until now we have done the questions, and this is the end of the PH and PI problems. Hope you have enjoyed it, and from now on I am thinking we'll discuss the question papers, and when we are discussing the question papers I will explain the concept if it is needed. So that will save our time. Thank you.